Is writing concurrent code difficult? Some might say, myself included, that learning how to write concurrent code is probably one of the more difficult endeavors that you'll encounter in your programming journey. And this is partly because there are many ways to go wrong with writing concurrent code, and there are only a few ways to really do it right. And in order to facilitate doing it right and avoiding the stress and everything else that comes with writing concurrent code the wrong way, I think that one of the best things you can do as a programmer is try to adhere to the patterns that have developed over time by more experienced programmers through lots of trial and error, as opposed to trying to reinvent the wheel. So in this video, we're going to go over an additional concurrency pattern, and this pattern is going to help you to write more robust and safe-proof and performant concurrent code. And for the sake of simplicity, we'll just call this pattern confinement, but it's really a way to make operation-safe code when dealing with multiple concurrent processes. And what I mean by that is this. If you imagine that we have multiple concurrent goroutines and all of these goroutines need to access the same segment of code, and that segment of code accesses shared resources. For example, if we have a value here that is subtracted from by multiple concurrent goroutines, this segment of code is called a critical section. And it's critical because if multiple concurrent goroutines are trying to access this same resource and we have no synchronization mechanism in place to ensure that the shared resource is accessed by one goroutine at a time, then we open the door for data inconsistency and or race conditions, which means that if two goroutines access this amount at the same exact time, they both see the same value for the amount and they both subtract 1 from that same value. And now the new value for the amount becomes whatever it was before minus 1. Well, that's wrong, right? Because two goroutines were trying to subtract from the amount. And that means that the current value should actually be whatever the value was initially minus 2. But the problem is, since both goroutines accessed this value at the exact same time, we had what is called a race condition. And this resulted in data inconsistency. So what we need to do to solve this is we need to synchronize goroutine access to this value. Now, a simple way of doing this is to guard the critical section by way of mutual exclusion, or in short, a mutex. And you can just think of a mutex as a lock. And before a goroutine can access a critical section, it needs to obtain the lock and lock off the critical section from other goroutines. Now, there's only one lock, so if it is currently being used to lock off the critical section, other goroutines will have to wait until the section is no longer locked off. Once the section is unlocked and the lock is released, another goroutine can pick up the lock and lock off the critical section. Now, this solves the problem of race conditions and data inconsistency, but it actually comes at a price to performance, and that's because a critical section is really a bottleneck to your program. Because remember, goroutines are needing to wait for the goroutine that currently has the critical section blocked off before they can continue with their work. So you can imagine if the critical section is a large segment of code that takes time to execute, that can add up to a lot of idle goroutines waiting around for the lock to be released. Okay, so before continuing with this video, I need to mention that I'm going into this expecting you to have an understanding of how pointers work in Go, as well as the basics of concurrency in Go. And don't worry, I have videos explaining both of these things. I have a short video that will get you up to speed with pointers in Go, and I also have a video on Go concurrency patterns, which is essentially the precursor to this video. And both of these videos are linked in the description. So yeah, without further ado, let's continue with this video. So let's have a look at another example of some code that might need to synchronize goroutine access to a shared resource. So this is just a simple Go program. It's just a main.go file, and of course the Go mod file. So if you're following along with this tutorial, just go ahead and create a main.go file, and we're just going to go ahead and create package main, and we're going to create our main function. And the first thing that we're going to do is we're going to declare a wait group. So we're going to use the sync package, and we're going to just use wait group. And if you don't know what a wait group is, it's quite simple. It's really just a way for us to wait for a collection of Goroutines to finish. And I'll show you more about what I mean by that in just a second. So we're going to declare this wait group here, and we're basically going to create sort of an input stream. And it's just going to be a slice of integers 1, 2, 3, 4, 5. And then we'll create a result slice as well. And this is also going to be a slice of integers, but this one we're going to initialize as empty. And what we want to do is we want to process this input stream and put the results into this result slice here. And for the sake of simplicity and for the sake of simplifying the understanding of this explanation, the only thing that we're going to do to process this slice here is we're just going to multiply each value by 2, and we'll just put the result value of each of these elements in this slice inside of the result slice. Now, the shared resource is actually going to be the result slice, and you're going to see what I mean by that in a second. So we'll go ahead and do a for loop, and for every element in input, we're going to first do wait group.add, and we're going to add 1. And we're going to need to add 1 to this wait group for every Goroutine that we spin up. And that's how the wait group's going to know how many Goroutines it needs to wait for. So we're going to spin up a Goroutine here, and we're going to call this function here called process data, which we haven't created yet. So we're going to create this function, and we're going to pass into this function the wait group. And that's because within the function, we're going to need to let the wait group know that this particular Goroutine is finished. Because if the wait group's waiting for the completion of all of the Goroutines that we spin up, each Goroutine is going to have to be able to communicate with the wait group and communicate that it's complete, so that the wait group knows that it doesn't need to wait for that particular Goroutine anymore. And again, you're going to see what I mean by this part in a second as well. So we're going to pass in a pointer to the result. Now remember, the result is the shared resource here. So we're passing in a pointer to the actual result that we have here. So within this process data function, we're going to be mutating the value of the result here. So we're going to be actually mutating this slice. So that's why we need to pass a pointer here. We need to actually access this slice that's outside of the scope of this process data function. And lastly, we're going to pass in the data, which is just going to be whatever value that we're at in the for loop here. Because remember, we're iterating through the input, and the input are these values, right? So for each call to process data, we're going to process one value in this slice. So there's going to be a Goroutine for each value in this slice, and each Goroutine is going to be processing its own value. And after this for loop, we need to do wait group.wait. And this is where we're actually waiting for the completion of the Goroutines that we've spun up. Because if we don't wait for them, we'll get through this for loop and these Goroutines will be running, and we'll still just, if we don't do this, we'll still just end the program. Like the main function would just end without waiting for the completion of the Goroutines. And again, if you're not really familiar with how Goroutines work, I suggest you watch my video on concurrency patterns in Go prior to watching this video. So we'll just add wait group.wait here. And lastly, we're just going to print the result. So by the time the main function completes, the result should contain every element from input multiplied by 2. So it should contain 2, 4, 6, 8, and 10. So now let's go ahead and create this process data function. So we'll just go up to the top here and we'll do func process data. Now this process data function is going to be the critical section of our code, because in this function, we're going to be accessing shared resources from multiple Goroutines. So remember, we're passing in the wait group, which is a pointer to sync.waitGroup. We're passing in the result, which is a pointer to a int slice, and we're passing in the data, which is an int. Now, this input, we're just reading from it, right? All we're doing is iterating through this input here, and then we're just basically giving this process data function a copy of the element from the input. So we're not mutating this input in any way. This isn't considered a shared resource in this case. So remember, the shared resource that we're dealing with here is this result. And the reason this is the shared resource is because this. So let's go ahead and write out the rest of this function here. So before we do anything, we're just going to defer wait group dot done. And all this is going to do is when this process data function completes, this done method is going to get called, which is going to tell the wait group that this particular Goroutine that is currently running this process data function is finished. And defer just means that we're deferring it to the end of the function. So it won't run until the actual function completes. And all we're going to do is we're going to set processed data equal to data times 2. And then we're going to take the result. We're going to dereference the result since it's a pointer, and we're going to append to the result. And what are we going to append? We're going to append the processed data. Now here, we're going to have multiple Goroutines trying to append their processed data to this result. And what you're going to see happen is you're going to see that we're going to get race conditions, and it's going to result in the result being inconsistent. So you'll see what I mean. I'll show you what it looks like in just a second. So let's go ahead and run this, and you're going to see when we print the result that there's going to be some weird behavior. So let's go ahead and open our terminal, and we do go run main.go. Now, as you can see here, we get 6, 4, and 8, and that's only 3 elements, right? But there's actually 5 elements that should have been processed and appended to this result slice here, but we only got 3, so that's not the correct behavior, right? So let's go ahead and actually just run this a bunch of times and kind of get a better idea of how many times we see inconsistencies with this data. So if I just type in forever here and then go run main.go, it's basically going to infinitely run this go run main.go command. So it'll just keep running here, and you'll be able to see how many times we're getting these inconsistencies. So as you can see here, the lengths of the actual result slice vary, and sometimes we're able to get the full result and sometimes we're not, but it's very inconsistent. It's not something that you could have in actual production code. This is very buggy. So this is the type of thing that we need to avoid. We need to avoid race conditions when accessing these shared resources. So if we just go ahead and stop that, we're going to go over the first way that we can actually resolve these race conditions. And as mentioned in the explanation at the beginning of this video, the naive way to resolve it in this particular case is to actually synchronize Goroutine access to the shared resource using a mutex. But as I mentioned before, remember, using mutexes are going to bottleneck your code, but it will resolve the issue of the race conditions. So let's go ahead and we're just going to do var lock, and we're going to do sync.mutex. And then let's go ahead and remove these spaces. We'll do lock.lock, and that's going to lock off the critical section. Then we'll do lock.unlock, and that's going to unlock the critical section. So basically, we'll encapsulate the critical section in these lock and unlock calls. So that's going to lock off the critical section the same way that I explained in the explanation at the beginning of this video. So now, if we go ahead and save this, and we go back to the terminal, and we'll do the same thing again, we'll just infinitely run this command. You can see that although not always in the same order, we're getting the process data, all of the process data appended to the result array. And of course, it's not in the same order because, the Goroutines are running concurrently. So whichever one gets the lock is the one that is able to append first, and the order might vary depending on which Goroutine gets the lock and stuff like that. But the point is, access to this shared resource is now protected by the lock when it's being mutated. So if we go ahead and in this, you'll see that we're always getting the values from the input multiplied by 2. So it's 2, 4, 6, 8, 10. Regardless of the order, we're getting the correct data here. But again, this is not a performant way to handle this, because let's imagine that process data is actually doing something time consuming. Like right now, process data takes constant time because we're just multiplying data by 2. But what if process data actually did something time consuming? So let's go ahead and see what that would look like. We'll do func process, and we'll just say data, which is int. And we're just going to do time.sleep time.second times 2. So we're going to process data is going to take 2 seconds, and then we'll just return data times 2. Now here, we're just going to call process and pass in data. And I forgot to put the return here, so it returns an int. And now let's actually put a timer on the main function here. So we're going to do start equals time.now. And at the end of the function, right before we print the result, we'll format .println time.since and pass in start. So this is going to print how long the function takes. More specifically, how long the main function takes. And let's first comment out the lock. So we'll comment out the lock because I want you to see the lock being the bottleneck. Like I want you to see why I'm saying this lock is a bottleneck. So we're going to comment out the lock. We know we're going to get inconsistent data, but let's just see how long it takes to run the function without the lock. So let's open the terminal and we'll just do go run main.go. And you can see that without the lock, it takes 2 seconds, right? And of course the data's not, there's only 4 items in this result slice and the data is not consistent. So we're just going to ignore that for now. I just want you to see the bottleneck here. So let's now reintroduce the lock. Save the file, and we'll go to the terminal again and do go run main.go. Now, as you can see here, it took 10 seconds now. And if you do the math, you remember we're spinning up 5 goroutines. We're spinning up a goroutine for each one of these elements in the input slice. And each goroutine is taking 2 seconds, and 2 times 5 is 10, right? So it's going to take a total of 10 seconds with the lock. And that's because the goroutines are needing to wait for the release of the lock. So one goroutine is going to get the lock and it's going to lock off this critical section. So all the other goroutines, they're not going to actually run concurrently. They're actually going to just wait for the lock. And the goroutine that has the lock for that 2 seconds, once it releases the lock, another goroutine picks it up, but it's only one other goroutine that can pick it up, and the other goroutines still have to wait for the lock. So we're actually needing to process the data synchronously. So in this case, using this synchronization method with the mutex is basically the same as just synchronously iterating through the data and processing it one at a time. Like we're not even necessarily using concurrency here, although we're using goroutines. So that's just an example of how this is bottlenecking our actual program. But now, finally, we get to confinement. Like confinement can actually improve the performance of this program by eliminating the need to use this mutex for the synchronization of access to the shared resource. So essentially what's going to happen is we're actually going to be able to process the data concurrently, meaning that instead of this program taking 10 seconds to run because each goroutine needs to wait for the lock and it takes 2 seconds per goroutine, it's going to just take 2 seconds for all the goroutines to run concurrently. And let's actually explore what I mean by that. So we'll go ahead and refactor this code to use confinement. And after that, I'll fill in any gaps in understanding that might come up when I'm explaining confinement while actually refactoring this code. And actually, I forgot to mention one thing that's important to understand when we're actually talking about using mutexes to synchronize goroutine access to a shared resource. So right now, even though we're using a mutex here, we're not necessarily using it in the ideal way, because if you look at this code here, you can see that process data is the longest running part of this code, right? But we don't necessarily need to have this result array locked off for access while we're processing the data. So right now, when the goroutines are waiting for the lock, they're needing to wait for processed data, and that's why they're needing to wait for such a long time. But actually, the critical section doesn't necessarily include processed data because there's no shared resource being accessed in processed data. So this isn't necessarily part of the critical section. Critical section is actually this. This is the critical section. So we could actually move the lock here, and this would mean that the lock isn't being held while this long running process data is happening, and that would also improve the performance of this code with the mutex. And although this video isn't necessarily about mutexes in the sync package, I feel like it's important to mention that, like, when you're actually needing to lock off resources, you should try to do it in the most optimal way possible. Like, if you have the lock being held up by things that don't necessarily need to be a part of what's locked off, then you probably need to refactor your code at that point. So actually, we'll go ahead and run this too, just might as well. So if we open terminal now, it's not going to take 10 seconds anymore because the Goroutines aren't going to need to wait for the processed data. They're just going to need to wait for when the lock is held and this actual shared resource is being updated, which should be relatively quick. So we'll do go run main.go. And you see now that it took 2 seconds. But that just brings me to another point that is necessary to understand. Like, there will be times where the code that's encapsulated in the lock is going to take a decent amount of time, like enough time to actually degrade the performance of your application to actually run. So this is why I'm trying to help you to understand ways that you can improve the performance of concurrent code in Go, and also ways that you can avoid using locks and mutexes completely, because at the end of the day, there's a good chance that they could potentially bottleneck your code. So let's get into confinement. So we're going to refactor this code to make use of confinement. So we'll go ahead and remove the lock here, because of course we're not going to use that anymore. And we're actually going to need to change a few things in this code. So for example, or for starters, the main function, this result slice, we're going to want to give it a specific size because we need the indexes. And you'll see what I mean by that in a second. So we're actually going to change this to result equals make. So we're going to use this make function here, and we're going to make a slice of int, and we're going to actually set the size of the slice to the length of the input here. So basically, you can use make to create a slice with a specific size. Like here, when we're creating this slice here, the size is pretty much undetermined from our perspective. But if we use make, we can create the slice with a specific size, which we're going to set to the length of the input. So we can go ahead and delete that one. And now we have a result slice that's the same length as the input slice. And now we want to actually use the index here. So before we weren't using the index because we were just putting this underscore here. This underscore is a placeholder for the actual index, but we can actually change this to I, which would be a variable containing the index of the input that we're currently at, the index that the for loop is currently at. And now here's the main part that we need to change. Like, a very quick explanation of what confinement is basically we want to confine the Goroutine to a specific part of the shared resource, essentially. So for example, like, we need to be able to concurrently append or write to this result slice here, right? So each individual Goroutine needs to be confined to an index in the slice. And it might be difficult me just explaining this right now while writing the code, but don't worry, I'm going to go over this in more detail after we finish refactoring this. So for now, we're going to set this to a pointer to the value at index I of result, which in simple terms, this is the memory address. We're going to pass in the memory address of the box that will hold the element at index I. And I know that sounds really confusing, but don't worry, I'll go over this further soon. So for now, we're going to change this to this, right? So that means we need to go to process data, and we actually just need to change this to a pointer to an int. And again, I'll explain further soon. And now we need to actually change process data as well. So of course, we're going to leave the deferral of the wait group .done method, and process data is still going to do the same thing. It's just going to call this process data, which takes 2 seconds or whatever. And then for result, this is where we're actually going to need to change. And actually, we're going to name this result destination because it's the destination of where we want to put the process data. So we'll do result dest, and then that just means result destination. And we're no longer using append here because now process data can't see the actual full slice. Before, process data wasn't confined to seeing only one index of the slice. Before, process data was able to see the entire slice. So there was no confinement before. But now we're confining process data to seeing only the index of the slice that it has access to from its parameters. So within this function's lexical scope, it can't access this result here because we're only passing in the actual location in the slice where we can actually put the process data. So we'll go here and we'll just delete that because now we're just literally setting this particular location to the process data. And I know it sounds really tricky right now. Like that's confinement, but I'll explain more, don't worry. So we're going to go ahead and just run this. Make sure we save first, and we'll do go run main.go. Now, as you can see, it's taking 2 seconds for us to process all of the data, and we get 2, 4, 6, 8, 10. So if we run this again, there will be no inconsistencies. It's gonna be correct every time. And actually, we can actually check and see if the code has race conditions by doing go run race, and we'll do main.go. And as you can see here, there are no race conditions. If there were race conditions, there would actually be some information printed to the screen here letting us know that there are race conditions in the code. So we can leave that. So that's confinement, but actually now it's time for me to actually explain to you what this actually means. Like why is this confinement? So let's get into that. Okay, so you'll recall that before refactoring the code to make use of confinement, we had this process data function here. And basically we were using the go keyword to fork off Goroutines to run this process data function concurrently. Now, before the introduction of confinement into our code, we were giving every Goroutine access to this entire result slice. So with multiple Goroutines, they were all able to see the entirety of this result slice. And they were all trying to append to the same result slice concurrently. So if you can imagine that all of these are running concurrently, prior to the introduction of the lock, we were getting race conditions because we had no synchronization mechanism in place to safely mutate this result slice. So in this case, every Goroutine can see the entirety of the result slice, and within this code, we can actually mutate the result slice. There's basically no restriction to what an individual Goroutine can do to this shared result slice. Now, confinement is basically the idea of ensuring information is only ever available from one concurrent Goroutine. For example, in our case, each individual Goroutine really only needs to be able to access a particular index of result because we're only storing the one value in the result slice. So if we can coordinate the indexes that each Goroutine can access, we can easily coordinate writing to this result slice concurrently. So let's explore this a bit further. So let's go ahead and draw out our result slice. Now remember, in the new code, we're giving our result slice an actual length this time. So now it's not just an empty slice, it's an empty slice with indexes that we can actually use as locations to actually store the process data. So right now, this result slice looks like this. So the indexes, all right in yellow here, we have 0, 1, 2, 3, and 4. And these are the indexes. And in Go, these are all going to be initialized with 0 values. So this is what this result slice looks like when we first initialize it. And for the sake of comparison, we'll put our input slice here, and the input slice has the same number of indexes, 0, 1, 2, 3, and 4. And the values in the input slice are 1, 2, 3, 4, and 5. Now, the reason we added the length to this result slice is because we want to have specific indexes that we can assign the process data to. So when we actually get to this for loop here, we're taking the index here and we're using it to determine which place in this result array that this data here is going to be stored. So for example, this data here, at the first iteration here, this data is going to be 1 and this index is going to be 0. So at the first iteration, this is the data in the index, right? So in our results array, we want to store the process data in the corresponding index in the result array. So the process data at index 0 here will be stored at index 0 in the result array. So we're passing in 1 here and we're giving the memory location of this particular index of the result slice. And if I make the mistake of saying array instead of slice, just ignore that. We're dealing with slices here. Anyways, so this here is a pointer to the index I at result. So for the first iteration, for example, this points here to index 0 of the result array. And since it's a pointer, this is the memory location of this part of the result array. So maybe the memory address of this index in the result slice looks like this. So when we're actually calling process data here and we're spinning up this Goroutine, we're giving this Goroutine not the entire result slice, but just the memory address of a specific index of the slice. So when we get here, this Goroutine is going to be confined to the lexical scope of this function, right? And within this scope, we no longer have access to the entire result slice. We only have access to the memory address of one index of the result slice. So we're only able to alter this one index. And here in this for loop, we're controlling which index this data needs to be assigned to at each iteration. So each Goroutine is going to be confined to their particular index. And that's what I mean by confinement. Basically, it's impossible for this Goroutine to access a different index in this slice, right? So there can't be a race condition because the other Goroutines, it's going to be impossible for them to access this index of this slice. They're all going to be assigned their own individual index of the slice, and they're going to be confined to writing to that index only. So this makes this actual code here concurrency safe. So we don't need to implement anything in regard to like mutexes. So since this is a pointer here that we're receiving, which is just an address in memory. And again, if you don't understand pointers, it's critical that you understand them for this video. So please go watch my pointer video. But yeah, since we're receiving the pointer here and then we're dereferencing it here and then assigning a value to that, in the case of the first iteration here, we're assigning the value to this index here. So it would be 1 times 2, which would be 2. And we're doing that for all of the indexes. And since the index of input and result are synced, we just need to iterate through input, get the index for input, and use that to assign the index for the result slice. So remember, confinement is the idea of ensuring information is only ever available from one concurrent Goroutine. So in our case, for the first iteration here, this index is only ever available from the Goroutine that we spin up at this first iteration. So the Goroutines that we spin up at subsequent iterations here, they will never be able to access this. And that's confinement. Each Goroutine is confined to its specific index of the result slice, and it can't access any other index. Therefore, we don't need to use any synchronization mechanism to ensure that we don't get race conditions, and we don't need to worry about the code not being safe for concurrency. And I hope that makes sense. Okay, so congratulations on making it this far. I know this is a relatively cumbersome topic and it's quite difficult to get through videos like these. So if you were able to make it to the end and you were able to learn something, then you're ahead of the pack in my opinion. But anyways, if this video was in any way helpful to you, or if you learned something valuable, please don't forget to leave a like. Leaving likes really helps out small channels like mine, and I put a lot of time and effort into these videos. So yeah, I'd appreciate it if you leave a like, and if you're interested in more content like this, feel free to subscribe as well if you haven't already. And with that, I will see you in the next one.